Imagine a world where machines quietly learn, adapt, and assist, not with noise or haste, but with a gentle intelligence that reflects human curiosity. This story will guide you through the evolution of artificial intelligence, from the earliest mechanical ideas and pioneering thinkers to modern learning systems shaping our daily lives. You'll explore how humans envisioned intelligence in machines, how simple rules and algorithms gradually transformed into systems capable of learning, and how AI has become both a tool and a companion in our modern world. Stay with this story until the end to follow the full journey of AI. You'll understand not only how AI works, but how it mirrors human curiosity, creativity, and the ongoing story of exploration and discovery. Listen, and don't forget to like, subscribe, and leave a comment sharing your thoughts and experiences on the incredible ways machines learn. Long before computers filled rooms or algorithms sifted through oceans of data, humans were fascinated by the idea of machines that could perform tasks like thinking, reasoning, or calculating. The earliest stirrings of this fascination were not electronic at all. They were mechanical. Ancient automata, intricate clocks, moving statues, and self-operating toys captured the imagination of inventors and philosophers alike. Each gear, spring, and lever suggested a world where the motions of machines might one day mirror the motions of thought itself. In the 17th and 18th centuries, mathematicians began formalizing ideas that would eventually support this vision. Blaise Pascal and Gottfried Wilhelm Leibniz developed mechanical calculators, demonstrating that arithmetic operations could be automated. Leibniz particularly envisioned a machine capable of performing not just addition and subtraction, but all arithmetic operations, laying the groundwork for abstract thinking about calculation and logic. These devices were primitive by modern standards, yet they carried the seeds of a profound idea that intelligence could, in principle, be expressed through precise, repeatable operations. The 19th century introduced perhaps the most significant figure in early computation, Charles Babbage. With quiet determination, Babbage conceived the difference engine, a mechanical calculator designed to automate the production of mathematical tables. Its gears, levers, and cogs performed addition, subtraction, and iteration with meticulous precision. Babbage then extended this vision with the analytical engine, a device intended to handle general computation through programmable instructions. While the technology of his era made constructing the full analytical engine impossible, his designs included components strikingly familiar to modern computers: a mill for calculations, a store for memory, and the use of punch cards for program instructions. Alongside Babbage, Ada Lovelace emerged as a visionary interpreter of his work. She recognized that numbers could represent more than quantities. They could encode patterns, relationships, and operations. In her notes on the analytical engine, she wrote of the machine's potential to manipulate symbols according to rules, hinting at possibilities that extended far beyond arithmetic. She imagined that a machine could, in theory, compose music, generate graphics, or explore patterns in mathematics, early glimpses of the creative potential of programmable systems. Her insights suggested that intelligence might not be confined to humans alone, but could, with careful design, emerge in machines.
While Babbage and Lovelace focused on practical and theoretical computation, other thinkers were drawn to the idea of machines that mimicked life. Automata of the 18th and 19th centuries, like Jacques de Vaucanson's digesting duck, astonished audiences by performing complex sequences of actions, simulating behaviors that seemed almost intelligent. These devices were mechanical, not cognitive, yet they inspired generations of inventors to consider what it might mean for a machine to think. Each turning gear became a metaphor for mental activity. Each programmed sequence hinted at the possibility of logic beyond human hands. By the early 20th century, the foundation for modern computing had been laid. Mathematicians such as Gottlob Frege and Bertrand Russell formalized logic, providing a language in which machines could, in principle, manipulate truth and inference. David Hilbert posed the challenge of formalizing all mathematics in a systematic, computable way. These theoretical breakthroughs suggested that reasoning itself might be expressible as a sequence of formal operations capable of being executed by a machine constructed from precise, predictable parts. Meanwhile, in practical terms, engineers were inventing machines that processed information mechanically, electromechanically, or electrically. Herman Hollerith developed punch card systems to tabulate census data, streamlining the processing of large amounts of information. Such machines demonstrated that the repetitive, structured handling of data could be automated, freeing human minds from tedious labor. They also hinted at a broader possibility. Machines could not only calculate, but also understand structured information in ways that resemble cognitive activity. The concept of a thinking machine took a decisive turn with Alan Turing in the 1930s. Turing formalized the notion of a universal machine capable of simulating any algorithmic process. His abstract theoretical model, now called the Turing machine, showed that computation could be generalized. A machine could, in principle, execute any sequence of operations that could be expressed in logical rules. Turing's insight bridged the gap between human reasoning and machine operation, laying a foundation for the entire field of computer science and ultimately artificial intelligence. Early attempts to build machines that could simulate intelligence were cautious and deliberate. Researchers explored symbolic reasoning, where rules and logic formed the basis of decision-making. Machines were programmed with explicit instructions to manipulate symbols, proving that computers could follow sequences to reach conclusions. While these early systems were rigid and limited, they offered proof of principle. A machine could perform tasks that required structured thought, providing a glimpse of the potential for intelligent behavior beyond human execution. Simultaneously, thinkers considered the philosophical implications of machine intelligence. Could a machine truly think, or was it merely simulating reasoning? These debates, quiet and theoretical at first, became intertwined with scientific and engineering practice. Researchers pondered whether intelligence required consciousness, creativity, or understanding, or whether it could emerge from the disciplined, precise manipulation of symbols and data. Even as machines grew more capable, these questions lingered, emphasizing the deep connection between human curiosity and the development of artificial intelligence. By the 1950s, the first programs that could perform rudimentary reasoning began to appear. Logic theorists wrote software that could prove mathematical theorems, demonstrating that machines could manipulate symbolic information in meaningful ways. These early AI programs, though primitive by modern standards, revealed a critical principle. Intelligence could be encoded as rules, patterns, and operations executed consistently and reliably by machines. The narrative of AI's early development is also a story of imagination. Researchers often envisioned machines as collaborators or assistants, capable of enhancing human problem-solving rather than replacing it. Early experiments in game playing, such as chess or checkers, programs illustrated that machines could compete with human thought in structured environments. Though the programs were limited, they inspired both wonder and ambition, showing that intelligence could, in some form, exist outside of organic brains. Learning, even at this stage, was mostly guided. Machines followed rules, checked conditions, and executed sequences. Adaptation was minimal. Programs did not improve themselves without human intervention. Yet the seeds were sown for the next stage of AI, systems that could modify their behavior based on experience, learning from data in ways that humans could observe but not explicitly dictate at every step. This transition from rigid automation to adaptive learning would become the defining characteristic of modern AI. The early decades of AI research were marked by both excitement and caution. Researchers explored problem solving, natural language understanding, and heuristic approaches to computation. They constructed programs that could simulate reasoning, navigate mazes, or interpret simple linguistic statements. While primitive, these systems demonstrated that machines could participate in processes once thought uniquely human, laying the groundwork for decades of exploration, refinement, and innovation. Even as machines became more sophisticated, the narrative remained gentle and exploratory. AI was framed not as a threat, but as a tool, a partner in the pursuit of understanding, capable of extending human capability and curiosity. Researchers approached the work with patience and care, iteratively improving algorithms, debugging code, and refining logic. Each experiment, successful or not, represented a step forward in the quiet accumulation of knowledge, illustrating how intelligence, human or artificial, is built gradually through repeated effort and observation.
By the mid-20th century, the theoretical groundwork laid by visionaries like Turing and Lovelace began to converge with practical innovations in electronic computing. Early computers, massive by today's standards, filled rooms with humming vacuum tubes, punch cards, and spinning tape drives. These machines, capable of executing sequences of instructions far beyond human patience, became the tools through which abstract ideas about intelligence could be tested in the physical world. Researchers marveled at the speed and precision of these early computers. A calculation that might have taken days of human labor could now be performed in seconds. Mathematicians and engineers recognized that computation could be harnessed not only to solve arithmetic problems, but to explore logic, reasoning, and even patterns within language and games. The concept of a programmable machine had evolved from theoretical designs to tangible, functioning devices, a new medium for exploring human curiosity about thought itself. It was during this period that the first AI experiments began to take shape. Researchers sought to encode human knowledge into symbolic forms that machines could process. Logical statements, rules, and heuristics were written into programs designed to emulate reasoning. These early systems could solve mathematical problems, play structured games, and even answer questions within limited domains. Though rudimentary, they demonstrated a remarkable possibility. Machines could, in some way, participate in processes once thought uniquely human. Chess and checkers became a testing ground for early AI. By programming rules and strategies, computers could compete with human players, though often in ways that were predictable and mechanical. Yet the very act of simulating decision-making highlighted the potential of machines to model thought. Each move, calculated with precision, reflected the application of logical principles to achieve an objective. These games, simple as they might seem, served as a microcosm for the broader pursuit of machine intelligence. Parallel to game playing, AI researchers explored problem solving in other domains. Programs were designed to navigate mazes, solve puzzles, and perform theorem proving. Logic and symbolic reasoning became central tools, providing a structured approach for machines to think. The challenge lay in encoding knowledge in ways that machines could interpret and manipulate, a delicate task that required both precision
and imagination. During these formative years, AI researchers encountered both promise and limitation. Symbolic systems could emulate reasoning within defined rules, but they struggled with ambiguity, context, and real-world complexity. Machines lacked the flexibility and adaptability inherent in human cognition. Yet each experiment revealed new insights, the nature of reasoning, the structure of knowledge, and the potential for machines to operate within complex domains if provided with sufficient rules and guidance. The concept of learning remained nascent. Machines followed explicit instructions. They did not improve themselves without human intervention. Nevertheless, pioneers began envisioning systems that could adapt, refining their performance based on experience or feedback. Early adaptive programs demonstrated the potential for AI to move beyond rigid rule following into a realm where patterns, data, and probability could guide behavior. The 1956 Dartmouth Conference marked a defining moment in the history of AI. Researchers gathered with a shared vision to explore the possibility of creating machines capable of learning, reasoning, and simulating intelligence. This event is often credited with formally launching the field of artificial intelligence. Enthusiasm was high, and researchers outlined ambitious goals, imagining machines that could translate languages, prove mathematical theorems, and even recognize visual patterns. The conference crystallized the collective ambition and optimism that would propel AI research forward for decades.
In the years following Dartmouth, AI research expanded into multiple approaches. Symbolic reasoning remained central, with programs encoding rules, facts, and logic to solve problems. Expert systems emerged, designed to replicate the decision-making of human specialists. These systems, while limited in scope, demonstrated that machines could store and apply knowledge in meaningful ways, assisting humans in domains such as medicine, engineering, and finance. Simultaneously, researchers explored probabilistic and statistical approaches. Early pattern recognition systems analyzed data to identify trends, classify objects, or make predictions. Though computationally intensive and constrained by hardware limitations, these methods hinted at the future of learning systems. Machines capable of adjusting behavior based on input rather than fixed rules. This represented a subtle shift in perspective, from rigid computation to adaptive intelligence, foreshadowing modern machine learning. Natural language processing also began to emerge. Researchers programmed machines to parse sentences, understand grammar, and respond to queries within restricted vocabularies. The limitations were evident. Machines could not yet understand context or nuance, and their conversation was mechanical. Yet these experiments laid the groundwork for future breakthroughs, demonstrating that even human language, complex and fluid, could be approached systematically by machines. Robotics became another frontier. Early machines were designed to manipulate objects, follow paths, or interact with controlled environments. While their capabilities were modest, they illustrated the potential for AI to engage with the physical world, bridging the gap between abstract computation and tangible action. Researchers observed that integrating perception, reasoning, and movement introduced new challenges, yet the rewards were clear. Machines could operate autonomously, executing tasks once requiring human intervention. As the field matured, limitations became apparent. Symbolic AI struggled with scale and uncertainty. Knowledge representation was labor-intensive, and real-world complexity overwhelmed rigid systems. This period, sometimes called the AI winter, saw reduced funding and tempered expectations. Nevertheless, these challenges were critical for the field's evolution.
prompting new ideas and approaches that would ultimately lead to learning systems capable of greater flexibility and adaptation. Through this time, the story of AI remained intertwined with human imagination. The desire to create machines that could learn, reason, and assist was driven by curiosity, problem solving, and a fascination with the nature of intelligence itself. Each experiment, success, and setback reflected the ongoing dialogue between human vision and technological possibility. The pursuit of artificial intelligence was not merely technical. It was a philosophical exploration, a gentle inquiry into what it means to think, to learn, and to understand.
The journey from early symbolic AI to systems that could learn required a shift in perspective. It was no longer enough for a machine to follow rigid, human-written rules. Intelligence, even in machines, seemed to require a capacity to adapt, to observe patterns, draw inferences, and adjust behavior based on experience. Researchers began to explore ways to encode knowledge that allowed machines to handle uncertainty, ambiguity, and the subtle complexities of the world. At the heart of this new approach were algorithms. Unlike static rules, algorithms could be designed to process data, recognize patterns, and generate outputs that were not explicitly predetermined. A simple sorting algorithm, for instance, could organize information in countless ways depending on the input. More sophisticated algorithms could search for solutions, evaluate possibilities, and learn from results, forming the basis of adaptive intelligence in machines. Data became the bloodline of learning systems. Early AI systems struggled because they had little information to work with. Every pattern, every decision, every inference required examples to guide behavior. Researchers realized that with enough structured data, machines could begin to identify regularities and make predictions. This understanding laid the groundwork for the emergence of machine learning, the notion that a system could improve its performance by observing and analyzing examples rather than simply following rigid instructions. Expert systems emerged as one of the first practical applications of this idea. These systems were designed to emulate the decision-making of human specialists in narrow domains. For instance, Mycin, developed in the 1970s, could assist medical professionals in diagnosing infectious diseases. By encoding knowledge from experts and applying logical reasoning, the system could suggest likely diagnoses and recommend treatments. While limited in scope, Mycin and similar programs demonstrated that machines could use structured knowledge and algorithms to perform tasks that required specialized intelligence. Rule-based systems, a close cousin of expert systems, provided another step toward learning. These systems stored facts and conditional statements, applying them systematically to derive conclusions. A rule might state that if a patient had a certain symptom and test result, a specific diagnosis was likely. Machines could follow these rules consistently and reliably, performing reasoning that was structured yet remarkably effective within well-defined domains. Pattern recognition represented a further evolution. Researchers began designing systems that could identify recurring features in data, whether images, text, or numerical sequences. Early image recognition programs could distinguish letters or simple shapes, while voice recognition systems attempted to parse phonemes and syllables. These programs introduced the idea that machines could extract meaningful information from raw data, forming the foundation for more sophisticated learning systems. At first, learning was heavily supervised. Human experts provided labeled examples, guiding the machine to understand which inputs corresponded to which outputs. For instance, in character recognition, a system would be shown thousands of handwritten letters along with their correct classifications. The machine would analyze features such as lines, curves, and intersections, adjusting its internal parameters to improve accuracy. This process was slow and painstaking, but it demonstrated a profound principle.
Machines could improve by observing examples rather than relying solely on pre-written rules.
Unsupervised learning introduced another layer of sophistication. In these systems, machines sought patterns and structures in data without explicit labels. Clustering algorithms, for example, could group similar items together based on inherent features, revealing hidden relationships. This approach allowed machines to discover insights independently, detecting trends and correlations that human designers might not have anticipated. Though less precise than supervised learning, unsupervised methods expanded the range of what machines could achieve. Neural networks, inspired by the structure of the human brain, became a transformative concept in machine learning. These networks consisted of interconnected nodes, or neurons, capable of transmitting signals and adjusting connections based on input. Early neural networks were simple, yet they revealed that machines could model complex, nonlinear relationships in data. By layering nodes and adjusting connection weights, these systems could approximate functions, recognize patterns, and adapt to new examples, hinting at the more powerful learning systems to come. The mathematics underlying neural networks was intricate, yet the principle was gentle in its simplicity. By adjusting internal parameters based on experience, a system could reduce errors and improve performance over time. Each input influenced the network's response, and each output was compared to a desired result. Discrepancies prompted small adjustments, gradually shaping the system's behavior. This iterative process, repeated across vast data sets, allowed machines to develop subtle capabilities that seemed almost intuitive. Machine learning also required careful consideration of representation. How data was structured and presented to a system could profoundly affect learning. Features had to be chosen, normalized, and organized so that algorithms could extract meaningful patterns. Researchers discovered that the quality and relevance of input data often mattered more than the complexity of the algorithm itself. A well-structured data set could enable relatively simple methods to achieve remarkable results, while poorly structured data could confound even sophisticated systems. The interplay between algorithms, data, and learning methods created a rich ecosystem for AI development. Researchers began experimenting with hybrid approaches, combining rule-based reasoning with statistical analysis, symbolic logic with neural networks, and supervised learning with unsupervised exploration. Each experiment provided insight into how machines could approach intelligence, not as a single process, but as a tapestry of interconnected methods, each contributing to understanding and adaptability. As systems became more capable, applications expanded. Early commercial AI appeared in business and industry, assisting with tasks such as credit evaluation, inventory management, and scheduling. These systems were often invisible, quietly operating behind the scenes, yet they demonstrated the practical value of learning machines. By automating repetitive reasoning and decision-making, AI systems allowed human workers to focus on higher-level judgment and creativity. Language processing, too, benefited from these advances. Simple parsing algorithms evolved into systems capable of identifying syntactic structures, extracting meaning, and generating text. While early systems were limited and rigid, they showed that machines could begin to handle the fluidity and nuance of human communication. These developments laid the groundwork for future breakthroughs in translation, voice recognition, and conversational AI. Throughout this period, the guiding principle remained gentle. AI was a tool for discovery and assistance, not a replacement for human thought. Machines could observe, analyze, and learn, but they were extensions of human curiosity and ingenuity. Researchers approached each project with patience, testing hypotheses, refining methods, and gradually uncovering the principles that govern adaptive behavior in artificial systems. Learning systems also prompted reflections on intelligence itself. By observing how machines acquired patterns, refined predictions, and solved problems, researchers gained insight into the processes underlying human learning. AI became a mirror for understanding cognition, revealing the structures, repetitions, and adjustments that support reasoning and knowledge acquisition. The interplay between human designers and learning machines highlighted the collaborative nature of intelligence, one guiding, one adapting, each enriching the other.
By the late 20th century, the foundations of AI learning systems had matured enough to support increasingly sophisticated methods. Neural networks, once a theoretical curiosity, began to demonstrate their potential for modeling complex, nonlinear relationships in data. Researchers discovered that layering nodes in multiple tiers, a structure now called deep learning, allowed machines to detect subtle patterns and correlations, far beyond the capabilities of simple rule-based systems. Each layer of the network transformed data in a slightly different way, passing its outputs to the next layer, gradually building a more abstract understanding of the information. This new approach was particularly effective in areas where human intuition struggled. Visual recognition, for instance, presented enormous challenges. Objects could appear in different orientations, lighting conditions, and contexts. Yet deep neural networks, trained on vast data sets of images, began to recognize patterns that mirrored human perception. A machine could identify faces, distinguish animals, or detect subtle anomalies in medical images. These systems operated quietly, tirelessly, refining their predictions with each new example, gradually approaching the subtlety of human observation. Language processing experienced a parallel transformation. Early symbolic methods had struggled to capture the fluidity and nuance of words, grammar, and meaning. Statistical approaches, combined with neural networks, enabled machines to analyze text and speech at scale. Algorithms could detect patterns in syntax, semantics, and usage, allowing machines to translate languages, recognize spoken commands, and even generate coherent text. Each success demonstrated the growing sophistication of AI, revealing the possibilities when learning systems process data in ways that were both adaptive and structured. In the world of decision-making, AI's subtle intelligence began to have tangible effects. Systems could analyze financial markets, predict trends, and optimize logistics. By processing large amounts of data and detecting correlations invisible to human observers, machines could suggest courses of action with precision and efficiency. These applications revealed a quiet power. AI was not only performing tasks faster than humans, but also uncovering patterns and insights that humans might never notice, complementing human judgment rather than replacing it. Reinforcement learning became another cornerstone of modern AI. Inspired by behavioral psychology, these systems learned by trial and error, receiving feedback in the form of rewards or penalties. A machine could play a game, navigate a maze, or optimize a process, gradually refining its behavior to maximize success. Over time, reinforcement learning enabled machines to develop strategies and solutions that were unexpected, sometimes outperforming human experts in structured environments. This method emphasized patience, observation, and adaptation, principles at the core of gentle learning. At the same time, AI research expanded into hybrid approaches. Symbolic reasoning was combined with neural networks, supervised learning with reinforcement methods, and probabilistic models with deterministic algorithms.
Each combination leveraged the strengths of different techniques, allowing machines to handle uncertainty, context, and complexity more gracefully. These hybrid systems could operate in dynamic environments, integrating knowledge, experience, and pattern recognition to support robust, intelligent behavior. Applications proliferated across diverse domains. In healthcare, AI assisted in diagnostics, drug discovery, and patient monitoring, quietly analyzing patterns in medical data to support clinicians' decisions. In transportation, intelligent systems optimized routes, predicted maintenance needs, and enabled autonomous vehicles to navigate safely. In industry, AI streamlined manufacturing, logistics, and supply chain management, adapting to changes and improving efficiency. Across these examples, the intelligence of machines remained subtle yet powerful, working behind the scenes to augment human capabilities.
Ethics and responsibility emerged as central considerations. As AI systems grew more capable, researchers recognized that learning machines could also reflect biases in data or design. Ensuring that AI systems operated fairly, transparently, and safely became a key concern. Gentle reflection on these challenges emphasized the collaborative relationship between humans and AI. While machines could learn and adapt, human guidance and oversight were essential to ensure positive outcomes. The expansion of AI into everyday life brought a quiet revolution. Recommendation systems suggested books, movies, and music tailored to individual tastes. Virtual assistants managed schedules, answered questions, and provided reminders. Search engines sifted through vast amounts of information to deliver relevant results almost instantly. Each application, seemingly simple, relied on layers of algorithms and learning processes quietly shaping human experience, with intelligence that was both adaptive and unseen. Machine learning also began to illuminate fundamental principles of cognition and intelligence. By observing how systems acquired patterns, generalized knowledge, and adapted to new situations, researchers gained insight into the processes underlying human thought. AI became a mirror, reflecting the mechanisms of learning, memory, and decision-making. The dialogue between human and machine was reciprocal. Humans designed and trained systems, and machines, in turn, revealed patterns and structures that deepened human understanding. Even in creative domains, AI began to demonstrate its gentle influence. Algorithms generated music, visual art, and text, exploring combinations and patterns that humans might not consider. These creative systems were not replacements for human imagination, but companions, extending the possibilities of artistic exploration. The learning process, observing, adapting, refining, became a form of quiet collaboration, where machine intelligence augmented human creativity. By the end of this half of Part 2, the subtlety and power of modern machine learning had become evident. AI systems were no longer limited to rigid instructions. They could learn from data, adapt to new situations, and operate in complex, uncertain environments. The evolution from symbolic reasoning to neural networks, reinforcement learning, and hybrid approaches demonstrated that intelligence could emerge through observation, adaptation, and structured learning. The journey was far from complete, yet the principles established in this period formed the foundation for AI's integration into human life. Machines could now observe, reason, and assist in ways that were both precise and gentle, shaping tools, processes, and experiences in ways that enriched human capability. Each advancement, each experiment, contributed to a quiet narrative, a story of learning, discovery, and the ongoing partnership between human curiosity and machine intelligence. This phase of AI demonstrated that intelligence need not be loud or overwhelming. It could be subtle, persistent, and adaptive. The machines of this era learned not through intuition, but through careful observation, structured feedback, and the accumulation of experience. By embracing these methods,
Humans and machines together open doors to new possibilities, expanding understanding and shaping the world in increasingly intelligent yet unobtrusive ways.
In the early decades of the 21st century, artificial intelligence quietly entered daily life. It did not arrive with fanfare or dramatic displays, but subtly, embedded in the tools, devices, and platforms that people used every day. Smartphones, email systems, search engines, recommendation platforms, and virtual assistants all began to employ learning algorithms that adjusted to user behavior, preferences, and patterns. AI became a silent companion, guiding actions, suggesting possibilities, and streamlining routines without overtly announcing its presence. Every interaction with technology became an opportunity for AI to learn. Each typed query, clicked link, or streamed video provided data that could be analyzed and processed. These data atoms, small fragments of human behavior, were collected, structured, and interpreted by algorithms that gradually improved performance. In this way, intelligence emerged not as a single entity, but as an accumulation of countless observations, each contributing to the system's growing understanding of human patterns and needs. Recommendation systems exemplified this subtle learning. Services like online streaming platforms, shopping websites, and news aggregators collected data on user choices and preferences. Over time, algorithms identified patterns in viewing, purchasing, or reading behavior, suggesting content or products aligned with individual interests. These systems operated quietly, often unnoticed, yet profoundly influenced how people discovered media, learned new information, and explored creative work. The intelligence of the system was cumulative, built on observation, repetition, and refinement. Virtual assistants brought AI into more interactive forms. Devices equipped with speech recognition, natural language processing, and contextual understanding could respond to questions, schedule appointments, and provide reminders. These assistants learned not only from their programming, but from ongoing interactions with their users, improving their ability to interpret requests, recognize context, and anticipate needs. In this way, AI became a conversational partner, a system that adapted to individual habits and preferences, gently easing the friction of daily life. Automation extended AI's presence beyond personal devices. Smart home systems, for instance, could adjust lighting, temperature, and security based on observed behaviors and environmental data. These systems were designed to learn over time, identifying patterns in activity and optimizing comfort and efficiency. Even though the machines themselves were quiet and unobtrusive, the effects of their learning subtly shaped daily routines, reinforcing the presence of AI as a constant, patient observer and facilitator. Transportation systems also began to incorporate AI in increasingly sophisticated ways. Traffic management algorithms analyzed patterns in vehicle movement, predicting congestion and adjusting signals to optimize flow. Navigation applications suggested routes based on historical and real-time data, learning from collective behavior to improve travel efficiency. In autonomous vehicles, in controlled testing and commercial applications, AI employed advanced perception and decision-making algorithms to navigate roads safely. In each case, AI operated with subtle intelligence, processing vast amounts of information to support smooth, adaptive behavior in real-world environments.
AI's presence in communication platforms quietly influenced the way people connected. Email systems filtered spam, prioritized messages, and suggested replies based on learned patterns. Social media platforms used algorithms to curate content, highlight posts, and recommend connections, learning from engagement metrics, preferences, and interactions. The intelligence behind these systems was pervasive, quietly shaping human interactions while adapting to evolving behaviors, interests, and contexts. Healthcare became another domain transformed by AI. Diagnostic tools, informed by machine learning, analyzed medical images, patient histories, and genetic data to support clinicians' decisions. These systems did not replace human judgment, but augmented it, providing insights, predictions, and recommendations that helped identify patterns invisible to the human eye. Algorithms learned from new data, refining their performance and improving outcomes in ways that were subtle, continuous, and adaptive. Education, too, saw the influence of AI. Personalized learning platforms adapted lessons to student progress, identifying strengths, weaknesses, and preferred learning styles. Systems could offer additional practice, alternative explanations, or pacing adjustments based on observed performance. Teachers could monitor insights provided by AI, using them to inform instruction while maintaining the human element of guidance, mentorship, and creativity. AI's learning was quiet, iterative, and supportive, enhancing the educational experience without overt intrusion. The integration of AI into finance and commerce was similarly transformative. Algorithms analyzed market trends, consumer behavior, and economic indicators, generating insights for investment decisions, risk management, and fraud detection. These systems operated continuously, absorbing vast quantities of data, learning from outcomes, and refining predictions. While invisible to most users, the intelligence of these systems influenced transactions, financial planning, and resource allocation, quietly shaping the global economy. AI also began to engage with creativity and content generation. Algorithms could compose music, generate artwork, and draft textual content, often in collaboration with human creators. The learning process involved analyzing vast data sets of existing works, identifying patterns and stylistic features, and producing outputs that reflected both learned knowledge and emergent originality. These systems operated patiently, iteratively refining outputs in response to feedback, exemplifying the gentle, persistent nature of machine learning. At the foundation of these applications lay layers of interconnected systems, each processing streams of data, identifying patterns, and adjusting behavior. Just as atoms combined to form molecules, these data units coalesced into intelligent structures, enabling machines to perceive, reason, and act. Each algorithm contributed to a broader narrative of learning, a quiet choreography in which countless small processes aggregated into meaningful, adaptive behavior. The subtlety of AI in everyday life often meant that users were unaware of the intelligence guiding their experiences. Yet the systems were constantly observing, learning, and adapting. They refined recommendations, improved recognition, and optimized decision-making, quietly weaving themselves into routines, habits, and workflows. This pervasive presence highlighted the essence of modern AI, intelligence that is patient, iterative, and embedded, shaping human life without demanding attention or acclaim. Collaboration between humans and AI became a recurring theme. Systems were designed not to replace human judgment, but to complement it. By handling repetitive, data-intensive, or pattern-based tasks, AI freed humans to focus on higher-level reasoning, creativity, and decision-making. The relationship was one of partnership. Humans guided, corrected, and provided feedback, while machines observed, learned, and adapted. The process was iterative, subtle, and continuous, reinforcing the gentle rhythm of learning shared between human and machine. AI's influence extended beyond individual interactions into societal systems. Urban planning, energy management, and environmental monitoring benefited from adaptive learning algorithms that processed complex, interrelated data sets. Machines could predict demand, optimize resources, and identify anomalies,
contributing to more efficient, resilient, and responsive infrastructures. The intelligence guiding these systems was quiet, yet its impact on collective human life was profound, demonstrating the capacity of AI to enhance society while remaining largely invisible in its operations.
As AI matured, a paradox emerged. Machines that were fundamentally silent and mechanical were increasingly responsible for creating systems that felt alive, responsive, and even creative. Algorithms trained on vast data sets could generate music, draft stories, compose visual art, or translate languages with subtlety that mimicked human skill. These outcomes were not the result of awareness or consciousness, but of careful observation, pattern recognition, and iterative learning. Yet to the human observer, the intelligence manifested in these outputs often felt organic, intentional, and meaningful. In many ways, AI's subtlety made its influence more profound. Unlike overt, clunky machines, learning systems often operated quietly, embedded in devices, platforms, and services, continuously processing data and improving without fanfare. The paradox lay in the contrast between the silence of their operation and the richness of their output. A recommendation engine, a generative art algorithm, or a natural language model could shape human experience, creativity, and knowledge while remaining almost invisible, a ghostly yet persistent intelligence. The question of consciousness inevitably arose. Could a machine truly understand the music it composed, the text it generated, or the patterns it recognized? Researchers and philosophers alike debated whether intelligence required awareness, self-reflection, or emotion. While AI lacked these qualities, it could nevertheless model processes that mirrored elements of cognition, learning, reasoning, decision-making, and adaptation. By observing these processes in action, humans began to see reflections of their own thinking, learning not just about machines, but about intelligence itself. Creativity, long considered uniquely human, became a collaborative domain between humans and AI. Artists and writers began experimenting with generative systems, feeding prompts, and shaping outputs through iterative refinement. The machine would produce variations, patterns, or compositions, and the human would select, adjust, and guide. This gentle interplay emphasized the complementary nature of intelligence. Machines excelled at exploring vast possibilities and identifying patterns, while humans provided context, judgment, and aesthetic sensibility. Creativity became a partnership, subtle, iterative, and profoundly productive. In science and engineering, AI's quiet presence amplified human capability. Computational models, simulations, and optimization algorithms assisted researchers in designing molecules, predicting physical phenomena, and exploring complex systems. Machines process data at scales impossible for humans, identifying correlations and solutions that would have remained hidden. In these endeavors, AI functioned as an extension of human cognition, quietly enhancing understanding and discovery without overtly drawing attention to itself. Education and learning were similarly transformed. AI-driven platforms adapted lessons to individual progress, providing targeted practice, feedback, and guidance. Each interaction collected subtle traces of behavior, which algorithms used to adjust content delivery. The process was iterative, continuous, and personalized. In doing so, AI revealed a gentle truth. Learning is a dynamic process enhanced when observation, adaptation, and guidance work in harmony, a principle applicable to both humans and machines. The integration of AI into daily life also revealed the interdependence of human and machine intelligence. Autonomous systems, intelligent assistants, and decision support tools relied on human-generated data
and oversight. Each human choice, action, or observation fed into the system, allowing it to refine performance. Conversely, AI's outputs informed human behavior, suggesting possibilities, highlighting patterns, and supporting decision-making. The relationship was reciprocal, forming a network of shared intelligence that spanned the organic and the synthetic. The subtleties of language further demonstrated AI's evolving capabilities. Natural language models learned from enormous corpora of text, identifying syntactic, semantic, and stylistic patterns. These systems could generate coherent prose, translate meaning across languages, and provide summaries or explanations of complex topics. The intelligence was emergent. No explicit understanding existed in the machine, yet the structure, repetition, and refinement of outputs reflected learning derived from patterns across countless examples. Human observers, reading or interacting with these systems, often experience a sense of presence, coherence, and insight that felt almost conscious, even though it was fundamentally statistical.
In the domain of vision and perception, AI began to interpret and analyze images and video at scales beyond human capacity. Systems could identify faces, detect objects, monitor environmental changes, and even anticipate movement or behavior. These capabilities relied on layered neural networks and pattern recognition algorithms, which adapted to diverse inputs through iterative learning. The intelligence was silent, but its impact was pervasive, enhancing security, accessibility, scientific observation, and artistic creation. Robotics extended AI's subtle influence into the physical world. Autonomous machines, drones, and industrial robots learned to navigate environments, manipulate objects, and optimize processes. Reinforcement learning allowed these systems to adjust behavior based on feedback, improving performance without explicit instructions for every scenario. The intelligence emerged quietly, through continuous observation, adaptation, and incremental improvement, transforming labor, exploration, and interaction in tangible ways. The combination of AI's adaptive capabilities and its subtle integration into daily life revealed a new dimension of intelligence: distributed, iterative, and emergent. Machines did not possess consciousness, intention, or emotion, yet their influence on human activity, creativity, and understanding was profound. They shaped decisions, guided exploration, and augmented problem-solving, creating a collaborative network in which human and machine intelligence intertwined. Even in artistic expression, AI demonstrated an ability to expand human horizons. Generative systems could propose musical variations, visual compositions, or narrative structures that humans had not previously imagined. The outputs were not understood by the machine, yet they provided raw material for human judgment, creativity, and refinement. The interplay created a quiet rhythm: machine learning, human selection, iterative improvement, a partnership that expanded the boundaries of what could be imagined, created, and experienced. In business and industry, AI's learning capabilities enabled more efficient, responsive, and intelligent processes. Predictive maintenance in manufacturing, demand forecasting in supply chains, and financial risk modeling all relied on systems that adapted to new data, identified emerging patterns, and suggested optimal strategies. Intelligence was expressed subtly through improved efficiency, insight, and decision support, rather than overt displays of computation. The quiet presence of AI became a cornerstone of modern operations, enhancing outcomes while remaining largely invisible.
Healthcare systems continued to benefit from AI's adaptive learning. Diagnostic imaging, genomics, and personalized medicine leveraged algorithms trained on vast data sets, detecting correlations and patterns beyond human perception. Machine learning improved predictions of disease progression, treatment efficacy, and risk factors. These applications demonstrated that intelligence could manifest in ways that were both precise and profoundly beneficial, quietly supporting human well-being and understanding. The integration of AI into society also brought ethical considerations into sharper focus. Bias in data, transparency of algorithms, and the potential consequences of automated decisions required careful oversight. Learning systems could amplify existing inequities or create unintended outcomes if not properly monitored. This underscored the importance of human responsibility. Even as machines learned and adapted, humans remained the guides, curators, and ethical stewards of intelligence in action. Education, healthcare, industry, creativity, and daily life together revealed the intimate interconnection of humans and AI. Machines learned through observation, pattern recognition, and adaptation, while humans provided guidance, judgment, and context. The partnership was iterative, ongoing, and subtle, demonstrating that intelligence need not be centralized or conscious to have meaningful impact. Quiet systems, learning continuously, extended human understanding and capability across domains previously unimaginable.
Artificial intelligence had quietly become a companion to human civilization. Once a distant dream explored in research laboratories, AI now infused everyday life, industry, and society. Its presence was often invisible, yet its influence was profound. From the algorithms managing urban infrastructure to intelligent systems optimizing supply chains, AI's subtle intelligence became a driving force behind efficiency, creativity, and discovery. In the home, AI adapted to routines and preferences. Smart thermostats learned patterns of occupancy and temperature preference, adjusting heating and cooling for comfort and energy efficiency. Voice-activated assistants responded to requests, organized schedules, and offered reminders based on observed habits. Each interaction, no matter how small, was a data point in a vast network of learning. Systems adapted quietly, iteratively refining performance to align with human needs. In industry, AI transformed operations with precision and foresight. Predictive maintenance in factories ensured that machinery ran smoothly, minimizing downtime and preventing costly failures. Logistics and supply chains became more efficient, guided by algorithms that analyzed demand, inventory, and distribution networks in real time. Machines learned to anticipate needs, optimize processes, and identify emerging patterns, quietly reshaping human workflows while remaining largely unseen. Education benefited as AI tailored learning experiences to individual students. Adaptive platforms monitored performance, identified strengths and weaknesses, and offered personalized exercises. Teachers could leverage insights from AI systems to inform instruction, focusing on areas where students required additional guidance or enrichment. Learning became dynamic and responsive, an ongoing conversation between human guidance and machine observation. Healthcare saw a profound impact as AI integrated into diagnostics, treatment planning, and patient monitoring. Algorithms analyzed medical images, genomic data, and patient histories to identify trends and make predictions. Machines could detect subtle anomalies, suggest interventions, and support clinicians in delivering precise, timely care. The intelligence was quiet but powerful, enhancing outcomes and extending human capability in ways that were both practical and life-changing.
AI's influence extended to scientific research and discovery. Learning systems processed massive datasets, uncovering correlations and patterns that eluded human observation. From climate modeling to materials science, AI became a collaborator, offering insights that accelerated innovation. Researchers used AI to generate hypotheses, simulate experiments, and refine models, creating a gentle yet persistent partnership between human intellect and machine learning. In creative domains, AI offered new perspectives and tools for artistic expression. Generative models produced music, visual art, and written content, providing inspiration and novel approaches for human creators. Artists could experiment with variations suggested by AI, refining outputs through human judgment. This partnership highlighted the complementarity of intelligence. Machines explored vast possibilities, while humans curated, interpreted, and imbued meaning. Creativity became a dialogue, iterative, adaptive, and collaborative. Societal systems also adapted through AI's learning capabilities. Urban planning leveraged intelligent models to optimize traffic flow, allocate resources, and predict patterns of movement. Energy grids became more efficient as algorithms anticipated demand and integrated renewable sources. Environmental monitoring used adaptive systems to detect changes in ecosystems, pollution, and climate, providing actionable insights for sustainability. Across these domains, AI operated quietly, observing, learning, and assisting in ways that were both pervasive and unobtrusive. As AI matured, its intelligence became increasingly distributed. No longer confined to isolated systems, learning algorithms interlinked across networks, sharing insights and adapting collectively. Cloud computing enabled vast computational resources to process data at scale, accelerating learning and enabling real-time adaptation. The intelligence of individual machines became part of a broader, interconnected ecosystem, amplifying impact while maintaining subtlety. Human experience continued to be shaped by AI in profound yet gentle ways. Personalized recommendations, predictive typing, and adaptive interfaces streamlined interactions, reducing friction and enhancing productivity. Social platforms employed algorithms to highlight relevant content, while search engines provided immediate access to knowledge across domains. Each application relied on learning systems that continuously refined performance, quietly influencing choices, preferences, and understanding. AI's evolution also highlighted the importance of ethical oversight in human stewardship. As systems became more capable, the potential for unintended consequences or bias increased. Researchers and practitioners emphasized transparency, fairness, and responsibility, ensuring that adaptive intelligence remained a positive force. The interplay of human judgment and machine learning underscored the collaborative nature of modern intelligence. Systems could learn and adapt, but humans guided, corrected, and contextualized.
As AI continued to evolve, the cycle of learning and adaptation became increasingly sophisticated. Each generation of systems built upon the successes, failures, and lessons of its predecessors. Machine learning algorithms, once modest in scale, now operated on massive data sets, refining predictions, improving decision-making, and continuously adjusting to new patterns. The intelligence of AI was no longer confined to specific tasks. It became a pervasive, adaptive force, quietly shaping processes across domains and disciplines. Autonomous systems extended the reach of AI into environments where human presence was limited or impractical. Self-driving vehicles, robotic exploration devices, and industrial automation all relied on learning systems capable of perceiving their surroundings, making decisions, and adjusting behavior in real time. These systems were designed to observe, evaluate, and adapt, quietly integrating into complex ecosystems and extending human capability into new realms. Quantum computing promised to accelerate AI's learning capabilities even further.
By leveraging principles of superposition and entanglement, quantum processors could evaluate vast combinations of possibilities simultaneously, enhancing pattern recognition, optimization, and decision-making. Learning algorithms adapted to this new computational paradigm, exploring previously intractable problems and uncovering solutions at scales unimaginable with classical computing. The future of AI thus combined the quiet persistence of adaptive systems with the extraordinary potential of emerging technologies. Collaboration between humans and AI remained central. Even as systems became more capable, they depended on human guidance, oversight, and contextual understanding. Ethical frameworks ensured that AI contributed positively to society, reducing bias, promoting fairness, and safeguarding privacy. Humans provided the moral and practical compass, while machines amplified the reach, speed, and precision of intelligence. Together, they formed an unbroken cycle of observation, adaptation, and application, demonstrating the ongoing partnership between organic and artificial cognition. AI's role in creativity continued to expand. Generative systems could propose novel musical compositions, visual artworks, and written content, offering new avenues for exploration and expression. Artists and designers interacted with these systems iteratively, selecting outputs, refining them, and incorporating human insight. This dialogue highlighted a fundamental truth: intelligence, whether human or artificial, thrives in collaboration. Machines could explore patterns and possibilities at scale, while humans provided direction, interpretation, and meaning. Creativity became a shared endeavor, quiet yet profound. Education, healthcare, and industry continued to benefit from AI's adaptive intelligence. Personalized learning systems refined instruction in response to student performance. Diagnostic tools in medicine improved accuracy and predictive capabilities. Industrial processes became more efficient, responsive, and resilient. Across these applications, AI operated unobtrusively, yet its impact was transformative. The silent intelligence of machines complemented human skill, extending capability and enriching understanding across all areas of life. The unbroken cycle of AI evolution reflected a broader pattern of learning and adaptation. Systems observed, processed, and acted, generating outputs that informed human decisions. Humans, in turn, provided feedback, guidance, and new data, enabling systems to refine performance further. This iterative process created a dynamic, self-reinforcing loop. Intelligence emerged through interaction, observation, and continuous adjustment. It was a gentle, persistent rhythm that underscored the deep interconnection of human and artificial cognition. Society began to recognize the subtle, yet pervasive influence of AI. Urban planning leveraged predictive models for infrastructure, traffic, and energy management. Environmental monitoring benefited from algorithms that detected subtle changes in climate, pollution, and ecosystems. In financial systems, AI models were embedded, distributed, and quietly influential, supporting human decisions while learning from experience. AI also shaped human understanding of intelligence itself. By observing how machines learned, adapted, and refined behavior, researchers gained insights into cognitive processes, problem-solving strategies, and pattern recognition. The study of AI became both a practical endeavor and a philosophical exploration, revealing the structures and dynamics that underlie learning in all forms. Humans learned from machines just as machines learned from humans, forming a continuous, reciprocal cycle of discovery. As technology advanced, new frontiers emerged. Autonomous agents could interact with complex environments, negotiate tasks, and coordinate with other intelligent systems.
Learning algorithms adapted to these multi-agent scenarios, discovering strategies, communication patterns, and cooperative behaviors. The intelligence that arose from these interactions was emergent, distributed, and collaborative, reflecting the dynamic interplay of observation, adaptation, and interaction. Quantum-enhanced AI further expanded potential. Optimization problems, simulations, and predictive models could now operate on scales and complexities previously unimaginable. Learning systems processed data in ways that leveraged quantum parallelism, exploring countless possibilities simultaneously. This new era promised a profound expansion of AI capability, enabling solutions to problems ranging from climate modeling to materials discovery and even to understanding complex systems such as human cognition or social dynamics. Amid these advances, the relationship between humans and AI remained gentle and deliberate. Systems were designed to complement human judgment, provide insights, and support decision-making. Ethical considerations guided design, ensuring fairness, accountability, and transparency. AI was not an autonomous force acting independently of human values. It was a collaborator, an adaptive partner that relied on guidance, oversight, and context to be most effective. The pervasive presence of AI across domains reflected a maturation of intelligence as a shared phenomenon. Humans provided creativity, insight, and ethical direction. Machines provided scale, precision, and iterative learning. Together, they formed a network of complementary cognition, each enhancing the other. This partnership was iterative, subtle, and continuous, a quiet force shaping the modern world.
The journey of AI illustrates the gentle, persistent evolution of learning systems. From early rule-based experiments to sophisticated neural networks, reinforcement learning, and quantum-enhanced models, AI has grown into a pervasive, adaptive partner in human life. Its intelligence is emergent, iterative, and subtle, shaping daily routines, creative expression, scientific discovery, and societal systems. If you've enjoyed this journey through the quiet, evolving world of artificial intelligence, take a moment to engage with it further. Like this video, subscribe for more immersive stories, and leave a comment sharing your thoughts about AI and its role in our lives. Your interaction helps continue the dialogue between human curiosity and machine learning, just as the story itself demonstrates.